Hello everybody and welcome to week 1 of our CAD class. Today we're going to take a quick introduction to Proteus. We're going to design a circuit that shouldn't be too awfully complicated for you, and we're going to really start in earnest to use this software as a tool. All right, so without further ado, let's jump into our slide presentation. So the first thing that I want to talk to you about is what makes Proteus special. Proteus is not the only piece of software out there. There are a lot of softwares available. Some of them are free. Some of them are extremely expensive. But Proteus kind of lands in the middle. It's not overly expensive, but it has a lot of powerful features that you don't see in a lot of the free software. So what kind of features do we get in a suite like Proteus or another professional software? It means that we can tie together our schematic, our bill of materials, and our PCB into one environment, so that when we make a change, it's seen an update across the entire design, as opposed to needing to go into the software and change the PCB, for example, because you changed something in the schematic, and then go into another piece of software to update the bill of materials. Now, this is a very powerful tool, but it's not flawless, meaning if I change, say, a footprint on the bill of materials or the schematic, the PCB will be updated, but possibly the traces won't be. So we need to actually be aware and go in and fix that. Another thing that Proteus will not catch is if you actually put in the wrong footprint, it doesn't help you. So you be very aware of garbage in, garbage out. Okay, Proteus is a great piece of software. I use it on a daily basis on my day job, as well as teaching it here at the college, but it does have its limitations as well. All right. So what we're going to do in this class is we're going to have a project. Basically, this entire class, the entire 14 weeks, is driving towards a final project. This project is a development board. The development board is great, in my opinion, because it allows us to see a lot of tools that we can use in Proteus, as well as a lot of concepts for electronics design, and some circuitry that's beyond your learning so far, but you're going to grow into it. And so what I'm asking for you to do is to remember that this is CAD class, not electronics class. We're going to learn some electronics, but basically you're going to be learning how to use the software, and anything that would be beyond the scope of your knowledge already for circuit design, I will provide for you, and you're just replicating it at this point. All right. So here is the circuit that we want to design. Daunting, right? There's a lot of stuff going on here, and if you don't take a look at this and go, holy smokes, there's probably something going on. You're either really good at circuitry already, or you don't understand the scope of what you're seeing here. But I want you to look at the little rectangles that I've drawn. Okay, there's one in the top left hand corner called PSU, and this is the power supply. And when you look at only that section, it doesn't seem too awfully bad, right? Instrumentation amplifiers, gulp. I mean, anybody that knows something about electronics knows that an instrumentation amplifier can become a bit of a bear as far as the circuitry, and you guys haven't learned anything about that yet. But you can see there's only half a dozen components, and so we don't worry about how to design it, but I give you some footprint so that you can work on it. The same with the microprocessor. It kind of gets broken down into these smaller subcircuits and really becomes consumable by the mere mortals that we are. One of the things that Proteus does allow us to do is to output a 3D file. And so here is an image of our file, and this is what we're going to actually complete for our year 1. The rest of it can be populated later, but in order to keep costs down, we only want to populate the necessary parts to show that the circuit board works at this point. Okay, and we won't get into the details of what each of these components are at this point, but this is the caliber of drawing that we're going to be able to create. Okay, so there are certain portions of the design that, like I say, I don't want to get into too awfully much, but know that it is broken down so that we have a power supply that provides us 3.3 volts. If you see any references to a 5-volt power supply, that was our first iteration a couple years ago, and I think I've got it all taken out. But if you do see something, flag it, send me an email and say, hey, look at slide 6 or something. Just let me know that I've messed up, and I will try yet again to remove anything. The microcontroller portion, so the MCU, we have a portion of that. To me, microprocessors are quintessential in today's electronics. There doesn't seem to be anything anymore that doesn't have a microprocessor in it. So I felt it's super important that we get a processor in here that you would be able to play around with. Some LEDs. Now, I think that you've already done like a Christmas tree or a stoplight or something like that. LEDs are ubiquitous. They're everywhere. And I usually have one on one of my circuit boards somewhere that's tied to a pin that allows me to do troubleshooting, at least in the first iteration or second iteration, and later can go away if I don't need it as a user interface. It is probably the easiest user interface to have. You can do a lot by flashing an LED. It can diagnose a lot of problems if you put in an error code. And so a simple button and an LED makes a good user interface. It's very economical and easy to use if you have the user manual. All right. We have a thermal sensor on here. One of the things that you're going to be using in several of your classes is a temperature sensor, and it allows us to actually start to convert things from analog to digital, and we're going to get into that in a lot more detail later. Rotary encoders and switches. We have one of them placed onto our board because it teaches us a lot about signal processing, so we'll deal with that. We do have the ability to put a keypad and an LCD on here, but I'm not going to require you to purchase those. But if you wish to go beyond what we're going to touch on in this class, by all means, I'll provide you files, and you can continue to work on at your own pace. There's also the instrumentation amplifier. As I said, it's there, and we're not going to get into too much detail on the design, but we are going to populate it electronically and simulate it. The same with the operational amplifier. You get into this a lot next semester, and so I wanted to have something available for you to start to play around with. Communications protocol. There's an RS-232 chip available. Again, it's something that you can populate on your own and start to communicate with your computer. For example, you could use the RS-232 through a bridge on your USB to talk back and forth between this peripheral and your PC. There is a slot on there for a Pro Micro. So if you did want to remove the microchip processor and put the Pro Micro, all of these hardware ancillaries are available to you through the Pro Micro. So if you want to program in C++ and use the Arduino IDE, feel free. Okay, and do remember though that it is now at 3.3 volts, so you're going to want to make sure that you have the 3.3 volt Pro Micro. There's also some auxiliary I/O. I/O stands for input output, and the idea here is that you would be able to basically hook this up to anything out there that is logic voltage levels. So we're looking at 0 to 3.3 volts, and you would be able to monitor whether a switch was on, or you could measure pressure or temperature via the analog inputs, and be able to control things via, say, a relay, be able to turn some lights on or off. And so this is really, for those in the electromechanical program, this is a PLC. Now the programming of it is not done through ladder logic. It will be through C or C++, which are your programming languages. And yeah, it's the heart and soul of a PLC. As I said earlier, the project is broken down into several pieces. The first is that we're going to design the circuit and simulate it piece by piece. We're then going to design a circuit board. You're going to actually do this. Once you've done that, then we can go in and create our bill of materials. You're going to purchase the parts yourself. So you'll notice that we didn't have a lab kit for this class. And so what I want you to do is either individually or as a group, order your parts from a reputable source. I don't recommend going to third or fourth party suppliers. Be careful of places like Banggood or AliExpress to order your parts. But DigiKey, Mouser, Allied, Electrosonic, there's numerous reputable sites that do sell legitimate ICs. You feel free to use any of them. And I want you to actually order the parts. Once you have your parts, you can assemble it. It's going to be difficult with our current environment to actually show this to the professor or get it programmed. But depending on what happens over the course of the semester with health restrictions, we're going to kind of play that by ear. But worst case scenario, you're going to have a circuit board, and I'll do my best to make sure that we have a way to program the microprocessor so that you can actually see the LEDs flash and do its thing. That said, everything does have to happen in a sequence. Okay, I don't want you ordering parts until we kind of sign off on it. I'm not going to give you a PCB until I sign off on your PCB design, and obviously I don't want to program it until you show that the power supply works. Right? We don't want to blow up the $3 microprocessor if our voltage supply is incorrect. All right. Okay, so now we can go ahead and jump into actually doing some work. And I want you to open up your Proteus, and we want to go through and make sure that we use the new project wizard. The reason for this is it creates a really nice border and frame, and I am going to show you how to create your own template. But for right now, we're just going to create a blank design using the project wizard. And I'd like you to call this new design in class exercise 1. All right. Okay, so we're going to use the wizard here. We're going to create a new project. As you can see, I'm using version 8.11, the latest service pack. Most of my slides are of a previous version, but anything that's new, I will augment with the new software. All right, so we want to go in and create a new project. This new project, we said we wanted to call this week 1 in class exercise. We'll say next, I want a landscape USA size. Okay, we're going to pick, we are going to use a PCB, although only so that I can talk a little bit about what all these buttons are. But we're going to go with a generic we'll go with default. Okay. Next, we're not going to mess around with the stack up layers at all. Okay, so we'll leave them and just click through all of it. We don't want to put any firmware in right now, and we'll finish up. And it should take us over to our PCB layout. Okay, so let's talk about what all these buttons do. And you can always come back to this portion of the video and look at this as a reference tool. Okay, so now that we've created our project, you'll see that we should have two tabs, one for the schematic capture and one for the PCB layout. The first thing that we want to do is actually go to the schematic capture, and we're going to talk about all of the buttons involved here. Okay. And so running across the top, a lot of these should look reasonably familiar, sort of Windows-based. You'll notice that there's a new open, save, close. Our home menu, which doesn't get utilized very much, but I do want to draw your attention to it. It is actually a great tool for to getting into some of the advanced features as for simulations and what have you. And we'll talk about that later. You can always create just a schematic or just a PCB layout. This is your 3D visualization. And so as long as you have a professional license, you are able to look at the PCB layout as we saw earlier. This next one is for your Gerber viewer. So we'll talk about that later, but basically it allows you to take a look at what the PCB manufacturer is going to see when they look at your CAD file. We have the Design Explorer, a super powerful tool. We're going to really get into this a lot. This one's for your bill of materials. This is source code. So if you do actually write code in Proteus, this is where you would access it. Project notes has been increased a lot in its utility. And so we're going to touch on some new material with that. And finally, the help menu. We'll just not comment too much on the help menu. As we move further across, we get into some of the buttons for how the environment's going to react. And so we have the wire router. Okay, we have the search tool. We have the properties assignment tool, possibly one of my favorite tools in Proteus. It allows us to change and manipulate certain fields. We have the ability to create a new sheet or delete a sheet. Basically, you're not limited to one page with Proteus. You can have multiple pages, and so we'll talk about that later. Variant selector. Sorry, I forgot the design rules button. So we're not going to deal with that too awfully much, but you are able to turn your design rules on and off so that you can do things that would be considered illegal by Proteus, and not get a raft of warnings saying that you had done this. But be aware that if you turn that off, those warnings are being created for a reason. Design variants. Design variants are great. We're really going to spend a fair bit of time working with that. But what design variants allows you to do is to have parts that may be used or may not be used on certain design aspects. So, for example, I may have a lot of parts that are used for a simulation or for testing, but won't actually be used in production. So I'll set up a different design variants. Okay. Next, we have the redraw design. Sometimes you'll end up with a situation in Proteus where you need to refresh the entire design. This is the button you go to. G is the hotkey for turning the grid on and off. If you ever lose your grid and you need to get it back, this is the button you would go to. False origin. False origin isn't used too awfully much by me in the schematic capture. I use it all the time when doing PCB layout, but it is there. Okay. So you've got your center your display. So if you ever find you're off in space somewhere and you need to center it, this is the tool that you use. And then finally we have our zooming. So you can zoom to a window, you can zoom in, you can zoom out, and zoom all. All right. Yeah, more Windows looking stuff. Undo, redo, cut, paste, copy. They're reasonably useful, but know that the cut and paste and copy can only really be used in a sheet. If you want to copy or paste or move blocks of text elsewhere, you need to use a copy to clipboard. So that's a little bit different. And then we have the block copy, block paste. Now, the nice thing about the block copy and block paste is that it will update your fields as you go. So you use this more for capturing entire chunks of text, or sorry, of design. Next is how we create parts and modify parts, and we're going to deal with that later. But basically, we have library parts picker. We have the ability to make a part, to make a package or modify a package, and to decompose or break apart a design. So basically, what happens here is if you have a design of a package, you can explode it, you can modify it and reassemble it, and then save it to your library for future use. Down the left-hand side, there's a series of buttons. We're going to touch on most of these, but there's a lot of detail here. So the ones that are really important today is you need to know your selection mode, you need to know your component, and we're probably also going to be dealing with some of the generators and tools. Okay, so here's your instrumentation, probes, and generators. Okay, so these are the ones that we're going to spend the bulk of our time on today. All right. Across the bottom, you have some buttons. You have the simulate button, so you can play, you can step through, you can pause it, you can stop it. Okay. Be aware that there's also a message area, and the processor. Don't worry about that too much. But in the bottom right hand corner, there is actually your XY coordinates. So be aware of that. More so when we start doing our PCB layout. All right. Okay, if you flip over to your PCB layout tab, you'll notice that a lot of the buttons are similar. We have our variant button. We have the redraw. Flip is interesting. So flip will let you look at your PCB from the back side as opposed to the front side. And so what difference does that make? Well, it just helps you lay it out if you're trying to put text in or something on the back side and you want to see what it looks like. You can flip it back and forth. Toggles the grid's the same. Layer colors and visibility. I caution you that I'd probably stay away from that right now, because if you manipulate it, you can mess things up quite a bit, but it's all recoverable. It makes it easier for me to troubleshoot if you leave it as your defaults, though. Okay. Metric and imperial is something that you're going to toggle back and forth between all the time. Metric parts, it's obviously easier to lay out in metric. Imperial parts in imperial. There's nothing to say that you can't switch back and forth on a regular basis. Unlike AutoCAD, where it was a bit of a bear to flip and flop between them, Proteus is seamless with that. The same with the false origin. Often I will pick a pin as my origin point and start laying parts out, especially when I'm mixing imperial and metric. All right. Polar coordinates over here, something that we're not going to use in this class, but know that it is there. Then we've got center and zoom functions. All right. Same deal, undo, redo, block copy, parts library. We can do all of the same magic as we could with the schematics, but with the PCB layout. The next section is unique to the PCB layout. So trace angle lock will allow us to basically make sure that all of our traces are either horizontal or vertical. We don't end up with some weird angles. This makes a really clean looking design, and it's recommended. Auto trace necking is something to be aware of. We want to be really careful with this, especially anything that draws a lot of power. You want to make sure that this is maybe not turned on. Auto trace selection, you should have turned on. If you need to put in a trace that is different than your design rules, this is where you would deal with that. The search button is very powerful if you're looking for a component and you don't know where you placed it. Auto name generator, we're going to get into that, but one of the nice things about Proteus is once you finish your PCB layout, you can select this button and it will renumber all of your components so that it makes sense on the PCB. So in case that I usually do, the top left corner is resistor 1 and resistor 2 is immediately below it, and so on and so forth. And it means that when we go to assemble our parts, it's easy to find a component. Okay. Okay, so the auto router and auto placer, they're here. We're going to talk about them. It's really important that we start off by not using them. Okay, I'm not going to insult your intelligence by not telling you that they're here. They definitely are here, and there is no such thing as a really good auto router. Okay, they do a reasonable job. Some are better than others. Proteus does okay, but there are certain things you need to be aware of. Okay, so one thing I never want to see is you throw a schematic together, auto place, auto trace, and send it out. It's almost guaranteed to fail. All right. The last button here is super important. It is the design rule manager, especially if you're going to be using the auto trace. You need to be aware of this and lay it out properly. All right. Now down the left-hand side, we have, again, a plethora of buttons to choose from. Today, we're not going to be using any of these, but know that you have this reference. If you're ever wondering what any of them are, you can use this, or you can just simply hover over the button, and it will give you a description of what it is. Okay, so a couple of them that we will pick or bring to your attention is the selection mode. Okay, you're definitely going to be using that. Track modes, you're going to be using that. And note that there is a difference between component and package. If I pick a package and I place it, it'll put just the package. It's not associated with the component. So if my resistor R1 happens to be a Res 40, and I pick a package called Res 40, I can actually create a schematic, but the component isn't linked. So Res 1 is R1 is a component that will be connected to, let's say, R2. You have to place those components or it won't actually create your PCB layout properly. Okay, across the bottom ribbon, we have our layers selector. This is really important to make sure that we're putting things on the right layer. For example, board edge. People always end up creating silk screen for their board edge and wonder why there's a problem. I'm telling you now, make sure that when you draw your board edge, it's in board edge. When you want to be in top copper, pick top copper. Okay. We also have a filter, so when we go to select parts, we can choose what kind of entity we're going to pick. All right, so let's flip back over to our schematic capture, and the first thing that we want to do is we want to start to pick some parts. Okay, so if you follow along on the slides here, we're looking to grab a 1N4148W, and so we can pick our parts here. So let's just press P for pick parts, or you can come over here to pick parts, and it will open up this menu. And from here, we can, there's a few ways that we can get there. We could actually do our sorry, where do we go? Pick parts. We can actually go to down here to diodes, and then we can go to 1N 4148. So there's 47, 41, 48W. And so we can double click on that. What else do we need? We need a 78 L33. And so maybe we don't know where to find that, what it's going to fall under. It's under an analog device, but we can actually type in 78L33. And you'll notice that it automatically pulls it up. It's a 3.3 volt regulator. So we'll double click on that. And so what else do we need? We need a red LED. Okay, so we can type in an LED. We can type in red, okay, with a space, and you'll see that it starts to narrow the fields down. And so here's a red active LED. So I'll choose that one. And what else do we need? We're obviously going to need a resistor. And there's two different symbols for the resistors, by the way. I'll just show you here. Okay, so there's res and then the IEEE symbol for a resistor as well. Either one, you can flip back and forth. I can show you later how to choose that you'll be able to get the European, the North American, or both of the symbols. But for now, I'm just going to select the IEEE. And we are also going to need a non-polarized, polarized and non-polarized capacitor. So again, we can start to look for parts. So we can go capacitor, take this out. We're looking for generic. And so we want a polarized and a non-polarized. I'm going to choose this one for my polarized, and I like that one for my non-polarized. And it's completely up to you. At this point, it doesn't really matter. This is just my technique. What else do we need? We need a connector. So the one that we're looking for, again, I've given you the detail, so you can actually type in the component that you want. So in this case, a SIL 156-02. There's all of one, and we're going to choose that part. And notice, however, when you're choosing these, if you press enter, it will select it and then close the selection menu. So then you would have to go back in and open it again to choose the next part. But that's okay. So everything in its place. And so now we're going to lay out a bridge rectifier. We're going to lay out basically the entire schematic. What we're looking for is we're going to create exactly this. And so I'll get you to pause the video, and I want you to recreate this schematic with the exception of these generators. Yeah, we'll kind of go through this step by step. All right. So pause the video. Come on back when you're done. All right. Okay, so now that we've selected the parts that we need, we're going to actually construct the circuit. And so the first thing that I'm going to do is I'm going to create my little bridge rectifier. So I'm going to grab my diode, and I'm going to go over here, and I'm going to place 1 and 2 that are going to be for the positive. And remember that plus and minus will allow you to rotate parts around, and Control M will allow you to mirror the parts. Okay. And so here I have these two diodes. They're going to create my negative rail, and these two diodes are going to create the positive rail. And then I want to connect the AC portion like so, create a bridge rectifier. And I'll just pull this out, and if I double click on one of the wires here, you can see that I'm able to just terminate my node like so. And so here we go. We've got our 4 bridge rectifiers. Next I'll go in and I'll lay in some electrolytic capacitor like so. And there's a couple ways that we can modify these values. One of them is to double click on the capacitor itself. And from here, we can actually type in that this is 220, and it's U instead of mu, but 220 microfarads. And then we've got a couple non-polarized capacitors. Okay, so I'll pop a capacitor here, and I'll pop a capacitor over here. And we've got our 7833 that's going to get placed here. Perfect. And notice that V in and V out are backwards for us. So we actually want V in coming in pin 3 and V out pin 1. And so I'll just highlight this part and Control M. I'll mirror it. And now V in is on the correct side. So there we go. And then we need a bulk capacitor. So we're going to grab another electrolytic capacitor. And I'll use plus here to rotate it around. And this one, instead of clicking on the part itself, I'm just going to double click here. And you'll notice that I can edit just that field. Okay, so in this case, 10 microfarad. This one is 100 nanofarad or 0.1 microfarad. And this one is 330. So you might ask yourself, where are these values coming from? The answer is the data sheet. They actually recommend these bypass capacitors. Great read if you're wondering about why you need to do that. Next, we have an LED. And yes, I realize that my PowerPoint presentation has a green LED and we're putting in a red one. It really doesn't matter. And I'll grab a resistor here. And we can join that guy up. So where does the value for this resistor come from? The answer is we need to do the calculation. So in this case, we need to draw a maximum full drive current of 10 milliamps at 2.2 volts. That doesn't mean that you have to run it at 10 milliamps, but that's where it's at its maximum brightness. Typically, I'll run usually about 80%, so I'll actually design around 8 milliamps instead of 10. But seeing as we're designing a 3.3 volt system today, you would use Ohm's law to calculate the resistor required for 10 milliamps at 1.1 volts or less. So in this case, I happen to give us a value, and I think 130 should be about right. So we'll connect this as we go across. And so a couple things that I can show you that are tricks, tips and tricks. Notice that when I connect this first one, if I double click the next one, I can place wires that are the same length. There's a caveat to this. If I just double click on another part, for example here, it will drop a wire that is the same length. Less useful. Okay. Another thing to bring up, you'll notice that when I double click on a part, so here we go, I'll put this here. If I double right click, I can erase a part. It's much faster than going in, right clicking and saying delete wire. Okay. And so here we go. I'll double click and all of these wires will be placed. Super quick, super friendly, and awesome. Okay. So this circuit would be finished normally, but we need to add a few instruments. We want to actually test this out. So let's go ahead and we're going to grab some virtual instruments, and I want to put in a AC voltmeter. It's very important that you pick the right type of voltmeter. Okay? If you put an AC meter on the DC side, you will only be measuring the alternating current for the AC component of the signal. So all of the DC gets filtered out, and vice versa. If you put a DC voltmeter on the AC signal, all you'll be measuring is the offset of voltage, okay, or the DC component. What else do we need? We'd like a voltmeter here, a DC voltmeter. So let's grab a DC voltmeter, like so. And we want to also have this funny resistor over here that doesn't seem to have any labels. And the idea of it is that we're going to simulate a load. Okay, so let's grab another resistor here. So, and a ammeter. Let's grab a DC ammeter. Okay. So, and the one thing that we want to do is we want to make sure that this never ends up as part of our PCB layout. And so there's a few ways that we can do it, but the easy way is to simply just get rid of the part reference. And then we can put on here, I don't know, 1K. So we're going to start out with 1,000 ohms as our load resistor. The other thing that we want to do is we wanted to get a voltmeter in here. And so one of the things that we can do when we forget something like this is to highlight our schematic like so, and then we can simply drag that portion. You'll notice that it opens up an area that we could drop in another voltmeter. So what I'm going to do is, rather than go over here and pick a voltmeter, I want to show you another tool. And so I'm going to highlight this part, and I'm going to go up and I'm going to choose block copy. And here we go. I'm just going to copy that over. All right. And then we can connect it like so. Perfect. Let's throw in some generators. Okay, so it'd be nice to have some power to this. So I'm going to go to sine. I'm actually going to feed in an AC signal, and we need a return for this signal. Okay. So, and by double clicking on the generator, we're able to access this sine generator properties menu. In here, we want to, the first thing is to turn off this icon, which hides all of our properties. The reason why we want to do that is we want to be able to take a quick look at it and see what's going on. The next thing is that we want to set our amplitude to 12, and we'll set our frequency to 60 hertz, which is the North American standard. And I'll say OK. And for the other side, we're just going to make it a return. So it's going to actually have an amplitude of nothing. Okay. So in essence, it's ground. Essence. All right. So we have 12 volts here. We have 0 volts here. We have a load resistor. We have an LED, and we have a regulator. So let's simulate it. All right. So notice that we don't have 12 volts here. We have we'll call it 8.5. The reason for that, remember, we set this to a peak, okay, an amplitude of 12. And so that's going to be 1 over root 2, so 0.707 times 12, which is going to come out pretty close to 8.5. Notice, however, that our DC voltage is higher than our RMS voltage, right? So, because this is actually measuring root mean squared. Okay? And that's because we're actually filling in the gaps with this bulk capacitor. And we're going to circle back around to what's going on in here by using a virtual oscilloscope later. Okay, so from there, we come in, we've got our bypass capacitor. Now this deals with any noise generated by the switch in here. And the same on the output. We have a bulk capacitor to take out any ripple and deal with any surges as things are turned on and off like switches. And then we have our LED, which doesn't appear to be lit up. So let's Let's dig into that a little bit further. And we also don't have any current, it appears, going through our 1K resistor. So let's start with this. We're going to go in here and I'm going to change this from amps. I'm going to drop it down to milliamps. All right. And so now we see that we actually have 3.3 milliamps, which if you think about it, we had a 1K resistor. So 3.3 divided by 1,000 would be 3.3 milliamps. And so that's spot on. But our LED's not showing up. And so let's grab a calculator and see what's going on with that. And so, as I said, we'd use Ohm's law and we'd calculate what we actually needed. So we have 2.2 volts, right? And so we want to actually subtract that from our positive 3.3 volts, okay? So, which leaves us 1.1 volts. And we want to divide that by, we were drawing 10 milliamps, okay? Which means that we should have 110 in here. And so that seems reasonable. We would expect that we would see some light here, but we will actually change this out, and we'll also check. Notice, sorry for the beep there. Notice that this does say for model type analog. Okay, so we're going to double check that this is an analog LED as well, and the model is digital. So there's our problem. We need to change this to analog. All right. So what's the difference between analog and digital? Basically, digital assumes, first of all, that you're running at 5 volts. So at 3.3, well, actually at 2.2, it's not really at that threshold. So if we set things to analog, it will do all of the math and all of the calculations associated with making sure that LED has a certain brightness. But when we get into more complicated simulations, if you don't actually care about it calculating the LED intensity, then you should set that to digital. Okay, so let's change this back to a 130, and reduce the current going through there now. And you'll notice it still lights up just fine. Okay, so that's easy enough. Okay, let's talk about your homework for a second. So far you've seen me change a couple things around to make sure that the LED was running. We've all seen that our circuit runs, and we're right now producing load through the load resistor at 3.3 milliamps. I would like you, with this design, to modify that load resistor so that you get 25 milliamps, 50 milliamps, 100 milliamps, and 250 milliamps. Okay. Now, caveat, I want you to do the calculations for what that load resistor should be. And I want you to run the simulation. And then using a screen capture, I want you to capture the image and show me what's actually going on at these currents. Okay. Take each of the screen captures, put it into a document, and I want you to save it as a PDF and put it in the Dropbox. All right. So a fairly easy lab this week. Just remember that it's the calculated resistor values. And I'll give you a hint. It doesn't exactly work the way they don't work. Okay. So, you're going to run into a problem. What I would like you to think about is why it might not have worked. I want you to hypothesize or create a suggestion as to why it failed, and think about what you might do to make the circuit work. And the reason for this is we're looking at how to use Proteus as a diagnostic tool and how to experiment with design concepts. Okay. So any questions, any comments, please feel free to email me. Send the email right away. I'm more than happy to respond. Same as last year. If there's anything that needs clarification, I'll try to make a video if it's something that the entire class might benefit from. But if it's something specific to you, I'll email you back right away with a response if I can. And yeah. Okay. So good luck, everybody. And have yourself a great week. Talk to you later. Bye now.